Ray Carnovale Limited. He is a graduate of the University of Toronto, a Bachelor of the Applied Sciences of Electronics in 1968. He received a Master's in the Business Administration, Schlick School of Business in 1974. From 1968 to 1970, he was a project engineer from RCA Limited, Montreal. In 1970 till 1974, he was a project engineer for CFRB Limited. 1974 to 75, he was the manager of engineering at Wardbeck Systems. 1975 to 78, transmission engineer, then chief engineer of Ontario. He did all this before I even started in broadcasting. From 1979 till 1997, he was the chief engineer and VP engineering, CFTO, VP engineering, then senior VP engineering of the parent company, Batten Broadcasting. From 1998 to 2001, he was the president of LeBlanc Broadcasting Incorporated. In 2001 to 2009, he was the vice president and the chief technical officer of Canadian Broadcasting Corporation, and is now retired. Ladies and gentlemen, Mr. Ray Carnovale.
Thank you. That's my Johnny Cash resume. So, my paper today is the determination of extended hours of operation of AM radio stations. Now, as you know, AM stations generally, most of them operate with different patterns, day and night, or different powers. I think it's also a well-known fact that a lot of stations in North America don't do what they're supposed to do at sunset. But this paper is going to explore how you can actually legally operate with your day pattern after local sunset. So what do we mean by extended hours of operation? Well, the Canada-US agreement states that extended hours of operation refers to the operation of AM radio broadcasting stations during the nighttime hours, which occur between 6 a.m. and 2 hours past local sunset time. And you have to adhere to the protection requirements in the agreement. During extended hours of operation, you must continue to provide protection to each co-channel station in accordance with Appendix 7, Annex 2, which is what we're going to drill into in depth. A station authorized for extended hours of operation shall not receive protection for that operation. So, in other words, even if your contour is, your interference-free contour is greater than you would normally have, that extended area is not protected. The usual rule for determining sunrise and sunset times for pattern change is the 15th day of each month, adjusted to the nearest quarter hour, and the power that you radiate during extended hours of operation shall not exceed the highest power that provides the required protection. So what does this mean in practice? Well, you might be able to remain on day pattern at full power for an extended period, or remain on day pattern at reduced power if it results in better coverage in important directions than your night pattern would achieve. For DA1 stations that operate with the same pattern day and night, but have lower power at night, you could remain on day power for an extended period. Or, in fact, you could operate at some intermediate power between your day authorized power and the night power. And if you have a DA2 antenna where you have a separate night pattern, but your phasing equipment is capable of accepting higher power, you might be able to operate the night pattern at higher power during the extended period. Conversely, pre-sunrise operation might be possible using the night pattern at increased power or the day pattern at full or reduced power. So why is this possible? Skywave propagation is not constant. It varies with time relative to sunset and sunrise. It also varies with frequency, being stronger for the higher frequencies than for the lower frequencies. And as you know, at the high end of the AM broadcast band, you often get daytime skywave propagation in the late hours of the afternoon in the winter. And normally, skywave protections are calculated without regard to frequency based on the propagation conditions that are assumed to exist at 2 hours after local sunset. So the normal procedure does not take into account the variation with frequency, does not take into account the fact that skywave propagation changes with time. The ionosphere consists of several layers. The D layer predominates in the daytime and is highly absorptive. The radio signals reaching it are not reflected. As sunset approaches, the D layer begins to dissipate, finally disappears, and as the layer dissipates, signals begin to be reflected by the F layer. In the daytime, the F layer is split into two layers, F1 and F2, but it becomes a single highly ionized layer at night, and that's what reflects the AM signal out to great distances. And excuse me, that the F layer reflectivity increases as night progresses, reaching a peak around midnight. So this is a simple schematic of the two layers. So in the daytime, you have the D and E, F1 and F2, but the signals are absorbed by the D layer. At night, you have the E and the F1 and F2 combined into a single F layer. So here's a prettier picture courtesy of NASA. So an important variable here that is the key to this whole derivation is the diurnal factor. That's a number less than 1 that specifies the ratio of the interfering signal at a time relative to sunrise or sunset as compared to the signal strength at 2 hours after sunset. There are two sets of diurnal curves, one for sunrise, one for sunset. And these are pulled out of the old 1982 Canada-US AM agreement. So on the left-hand side, we have the diurnal factors for sunrise, and on the right-hand side for sunset. The x-axis here is the frequency in megahertz, so we're looking at 500 kilohertz at the left, 1600 kilohertz on the right, which is where the AM band ended back then. And this shows the variation in the diurnal factor at sunrise. So at 500 kilohertz at sunrise, the diurnal factor is 0.15. So in other words, the skywave propagation at that point in time at sunrise is only 15% of what it would be 2 hours before sunrise. If you look at 1600 kilohertz, however, the diurnal factor is up around 0.3. Similar set of curves for nighttime. And again, at sunset, it's about 0.14 at 500 kilohertz, and it rises up to about 0.38 at 1600 kilohertz. So the diurnal factors are not the same relative to a given offset from sunrise or sunset time. They're different for the morning than for the evening. So how do you determine if extended hours of operation is possible? Well, the Canada-US agreement has a very arcane procedure. It was originally derived to permit post-sunset operation of Class B, C, or D stations located east of protected Class A stations. The Oxford Dictionary defines arcane as understood by few, mysterious, or secret. It can also refer to requiring secret or mysterious knowledge, and you will see why momentarily. So there are several steps that we have to go through. We have to determine the protection requirements to other stations and the actual radiation using the desired pattern. So if we're going to use the day pattern at night, we do a skywave analysis, but using the day pattern instead of the approved night pattern. We need to determine local sunset at the interfering station, determine the midpoint of the path between the points of protection for the protected station and the station desiring extended hours of operation. Now, the midpoint aspect is important. Normally, we don't consider the midpoint when we're calculating protections. We determine the protection for Class B, C, and D stations on a site-to-site basis. For Class A station on a site-to-contour basis. And after we determine local sunset at the midpoint, we need to calculate the time difference in minutes between the proposed pattern change time. Now, I know the answer here, it was 29 minutes, so if it's 29 minutes after local sunset at the interfering station, we compare that to the sunset time at the midpoint, and that tells us the sunset plus X quarter hours or minutes that we need to calculate the diurnal factor for. So once we determine the diurnal factor, we can divide the required protection by the diurnal factor, and because that's a number less than 1, it means we can actually increase the amount of radiation towards the protected station. So Annex 7 says that you calculate, the diurnal factors are calculated from the formulas contained in 2 tables of Annex 2 and represented graphically in figures 5A and 5B. Those are the 2 figures that I showed you earlier. So again, it's expressed as a ratio of the skywave field strength at any time during the pre-sunrise or post-sunset period relative to 2 hours past sunset at the midpoint. So here's a little ditty that's buried in the treaty. When a point in time relative to sunset or sunrise does not fall directly upon one of the curves, and it won't, calculations are made using the values on the curves that are adjacent to the time in question. These values are then converted to log values for linear interpolation at the required time. The anti-log is then taken to obtain the desired value. So this is the arcane part. I was scratching my head for a long time, trying to figure out what this really meant in the calculation procedures so I could arrive at repeatable results. And linearly interpolating a log and then going back to a log and then finding the anti-log was what I was scratching my head about. So to allow for a precise determination of sunset diurnal factors calculated to each minute, the formula on page 26 of the treaty was used in conjunction with this table. So this is the sunset diurnal factor table. There's a similar one for sunrise. So you can see that this corresponds to each of the curves that were shown earlier, quarter-hour increments. And what we have is what's known as a cubic equation. It's cubic because you've got an x factor, an x squared factor, and an x cubed factor. And the only variable here is frequency. All these other constants, A, B, C, and D, are specified for each quarter hour. So at sunset, at 680, the diurnal factor is 0.18357. I scoured high and wide on the internet to try and find where did this set of variables, where did this methodology arise? Because there's been all kinds of research done on skywave propagation, and I couldn't find it anywhere. It's really first referred to in FCC Notice of Proposed Rulemaking in 1983, and it was shown in the 1982 Canada-US Agreement. But other reference documents, like a 1967 exchange of letters between the two administrations that might have referenced it, couldn't find it. So once you determine the precise values of F diurnal for 680 for each quarter hour period, you then can calculate how that changes over a 15-minute period. So in this case, suppose we want to create a table showing the change in diurnal factor from sunset plus 15 minutes to sunset plus 30. Well, we end up with two diurnal factors, which give us two log values. So at sunset plus half an hour, it's minus 0.42141, and at plus 1 quarter hour, it's minus 0.55763. So we end up with a difference of two log values. We then need to interpolate that linearly. So if we're looking at 19 minutes after sunset corresponds to 4 minutes after the sunset plus 1 quarter hour. So we now take 4/15ths of a quarter hour, which is 0.2667, multiply the difference in log values, this value up here. If we multiply that, we now get log value differential for each minute. And then we do a subtraction, and remember that when you subtract negative numbers, you reverse the signs. So the revised log value is minus 0.535971. We take the anti-log, and there's our diurnal factor, 0.29109. So I use this approach for every minute created a big spreadsheet for sunset minus 2 hours to sunset plus 1 3/4 hours. And that replaces the graph with a precise per minute diurnal factor. So we're not squinting, looking at lines on a very blurry graph and trying to mentally interpolate values, which somebody else, like somebody at the FCC looking at the request, may not come up with the same value. So once that spreadsheet is derived, it'll work for any frequency because X is the only variable. So we can just punch in any frequency in the AM band and it spits out a whole new set of diurnal factors. Now, according to this arcane procedure, you determine the sunset time at the midpoint based on referring to a graph which has the north latitude in degrees, and then the times are over here. And it says, okay, once you determine what latitude you're at, you take the sunset time off the graph, but then you need to adjust it by 4 minutes per degree of longitude relative to the standard meridian at 90 degrees. So that gets messy again because there's, as you can see, there's really no resolution in this graph. So decided to use 2 online tools. I hope I'm still connected here. I am. So I found a tool for calculating the midpoint distance, and it's this tool. You just enter the latitude and longitude for each point, and over here it gives you the distance to a tenth of a kilometer, and it gives you the midpoint coordinates. So this is very repeatable. These results were actually virtually identical to what the VSoft AM Pro software calculates for azimuth and distance. So now we need to calculate the sunrise or sunset time precisely. And there's another online tool from the Department of Commerce in the United States. So if we go over here and say enter lat long, and then we can, there are some numbers already entered here. They were for Boulder, Colorado. And we want to calculate the sunset time relative to the Eastern time zone. So I changed this to 5 hours. And all pattern change times are referenced to standard time, not daylight time. So we leave this set to daylight saving time. We change the date to December 15th and calculate. And there we are. So the apparent sunset is, remember this is Boulder, Colorado coordinates that are in there. It would be 6:36 p.m. Eastern time. And sunrise would be at 9:16 a.m. Standard Time, Eastern Standard Time. So now we have a precise methodology for determining the midpoint and the local sunset time at that midpoint. We then take that local sunset time at the midpoint, reference it to the local sunset time at the interfering station, and that time difference is related to the local sunset, so it becomes sunset plus X minutes. So here's a real-world example. CFTR 680 in Toronto operates 50 kilowatts DA2, different patterns, day and night. That day pattern happens to have two very tight arcs of protection to nearby co-channel stations. So there are ground wave protections in New York State and I think Tennessee. So does this pose a possibility for extended hours? Well, using Vsauce software, we do a night protection analysis, but plug in the day pattern instead of the night pattern. And then produce a margin report. So this report here shows the call letters of the stations, and the red indicates that we have a negative margin. In other words, we would violate protections using the day pattern without taking into account the diurnal factor. So there were a total of 8 stations, 2 Class A's, clear channel stations, 1 in Barrow, Alaska, 1 in San Francisco, and 6 Class B, C, or D stations. All these other stations that are in green indicate that the day pattern fully protects those stations at any time at night. Here's a comparison of the 2 radiation patterns for CFTR. On the right here is the night pattern, the normal night pattern, and you can see the protection limits here. This is skywave protection to the skywave coverage of Barrow, Alaska, and this arc is the skywave protection to KNBR in San Francisco, and then we have the 6 other stations contained over here. So if we look at how the day pattern violates, you can see we have an overlap here, we have an overlap here, and 6 other stations that are contained in this arc. So if we divide the permissible radiation by the actual radiation, that gives us a ratio which is effectively the diurnal factor that must not be exceeded. Again, it's the diurnal factor for the midpoint of the path. So if we use the calculation tool in the local sunset at CFTR on December 15th, 4:44 p.m. So if we want to delay for 29 minutes, the pattern change time would be 5:13 p.m. So what does this mean relative to the midpoint local sunset? Well, the midpoint sunset times are shown over here in this column. What does that mean in terms of diurnal time in minutes? So it turns out that, first of all these greens here are where it's green across an entire row. Those are stations where the day pattern fully protects at night. So these are the 6 stations where we don't meet protections, and this is the diurnal factor that occurs at each path midpoint relative to the protected station. It turns out that our worst case Protection is a little station in Escanaba, Michigan, WDBC. And when we apply the diurnal factor, we actually end up with permissible radiation of 905 millivolts compared to the normal permissible night radiation at 2 hours after sunset of 263.59. So take the difference between actual and permissible, and we have a margin, a positive margin of 9 millivolts. Not much, but the law is the law. So protection to Class A clear channel stations is more complicated because instead of determining a single midpoint location using site-to-site distances, we have to determine the worst case, shortest distance to the protected ground wave or sky wave contour, which at night is the half millivolt contour for skywave stations. There are actually rare instances where a pattern has a deep minimum and the ground conductivity is high that the ground wave contour can outrun the skywave contour. Doesn't happen often, but it's a subtlety that has to be checked for. So this is the determination of the protection to KNBR in San Francisco. This is the half millivolt protected skywave contour, and the red here is the interfering 25 microvolt contour from the CFTR day pattern. So we calculate 3 points of protection on the contour. In this case, the midpoint sunset time is quite a bit later than it is in Toronto, so the diurnal factors are extremely low, and therefore the protections are trivial. We end up with margins all the way up to, well, from 5,000 millivolts per meter to 25,700 millivolts per meter. So that's trivial. Barrow, Alaska was a little more complicated. The skywave contour goes out over the Arctic Ocean, so we're only interested in protecting this part here. So we chose 3 points. Oops. And did the same calculation as we did for KNBR. And again, the diurnal factor, it's a lot higher. It's between 0.42 and 0.57, but we still ended up with a very large margin of protection. So the conclusions. The calculations resulted in a proved delay of 30 minutes relative to the normal sunset time specified in the technical operating certificate. Our calculation was based on 29 minutes, but because it's rounded to the nearest quarter hour, we were approved for 30 minutes. So the practical reality here is that the pattern change in December is at 5:15 p.m. Eastern Time instead of 4:45. And in June, it's 8:30 p.m. Eastern Time, which is 9:30 p.m. Daylight Saving Time, instead of 8 p.m. standard, 9 p.m. daylight. So this is of considerable benefit to drive time reach during about 8 months of the year, because your drive time audience is, in a place like Toronto, it's probably 4 to 7 p.m. So if you get an extra half hour after the sun has set, you're getting a larger audience reach. In the case of this pattern shape, and I'll jump back to it in a second, there was, you'll see that the lobe to the southwest and towards the west is actually what covers Oakville, Burlington, Hamilton. So a lot of commuters on that route. We checked to see if there would be a possibility of having an earlier morning pattern change, but given that we're east of the protected station, there was no real advantage. So just going to skip back. Okay, so you can see here on the pattern, the transmitter site is in Grimsby. So this area, this arc here, where my arrow is, that's what covers Oakville, Burlington, Hamilton. And you can see that it's a lot more signal than we have here, and no deep nulls, which cause sideband distortion. So that was the benefit. Again, every station is unique. So the analysis, there's no one-size-fits-all solution. It takes a separate analysis for each station. So that's my presentation. Any questions?
Hi, Ray. I have a question. One of your first slides talked about the agreement, and it said from 6 a.m. till sunset. So does that mean that in the summer when the sun's getting up earlier, I can take the earlier time, but in the winter when it's getting up later, I can still go to day pattern at 6 a.m.?
Well, that 6 a.m. I think is a reference to an FCC ruling that came about for daytime only stations, where they were allowed to sign on at 6 a.m. With their daytime facilities. I think that may have been rescinded. I'm not sure, but it never applied in Canada.
Okay, thanks.
Any other questions?
Hi. So what's the process to get that approved? Do you submit that to ISED and they get agreement from FCC?
Yeah, and it actually didn't take that long. The FCC protocol is that they're supposed to respond to notification requests within, I think, well, call it 30 to 60 days, preferably 30. And they turned it around very quickly. There was no objection or questions whatsoever. So what was involved was, in order to explain why I was using modified methodology from the treaty, is I had to walk through the entire process. So the application I presented to ISED was essentially what you see here as far as, okay, how do we determine the diurnal factor on a minute-by-minute basis? How do we determine the midpoint sunset or sunrise time accurately and repeatedly?
There's one at the back here. Go ahead.
Hi, sir. Good morning. Related to the question of Larry, so is there a difference on the pattern or the diurnal factor for an ordinary sunrise or sunset compared to sunrise on summer, sunset on summer, sunset or sunrise on winter?
Sorry, I didn't quite
Uh,
get the question.
is there a difference in the pattern or diurnal factor for like sunrise, sunset, or sunrise, sunset on summer, sunset, sunrise on winter?
Is any difference in the pattern? No,
Yes,
no,
sir.
there's no adjustment to.
I think he's talking about your diurnal curves.
Oh, no, the curves. The curves don't change relative to the time of year, and therefore the offset that we calculate that's permissible based on the diurnal factor is a constant offset for each month of the year. The pattern change time that's specified in your technical operating certificate. So it doesn't change. And, you know, you raise an interesting point because the research out there shows that there are actually a lot more variables that deal with skywave propagation. The latitude has been determined to be a variable. The magnetic patterns of the Earth. And of course, we know that solar flares can wreak havoc with any part of the telecommunication spectrum. So this is a good procedure, but it's not actually omniscient. And but you know, all these AM rules. Go back to, they were derived in probably most of them in the late 1930s, early 1940s, just as the NARBA agreement was being formulated. The bottom line is they may not be super accurate, but they have served us well.
Just curious as to whether or not the FCC would approve this change for stations south of the border, and if so, what happens if you've got two co-channel signals that both want to run that extra half hour?
Well, again, the treaty says that it's unprotected, and in fact, U.S. stations can do it, and probably used it more. To my knowledge, the FTR is the one and only in Canada that has an extended hours authorization. The procedure has existed in the United States for a long time, but it was meant primarily for domestic reasons. But the treaty actually shows as the example, which is not a very good example, protection to CBF Montreal on what was then 690. So it's unprotected. So if two stations want to do it, and yes, it increases theoretically. Well, actually, when you think about it, if the diurnal factors are accurate, it shouldn't increase the interference markedly. Interesting thing about the Escanaba protection, because they are located west of CFTR, they're still on day pattern for 20 of the 30 minutes. So they're operating higher power. They're operating 6 kilowatts in their day pattern for 20 of the 30 minutes that CFTR is staying on the day pattern. So it's also self-mitigating in that respect because their pattern change time is later.
Charles, Ray, I want to thank you very much for being here this afternoon and giving your presentation. On behalf of the CCBE, we'd like to give you this.
Oh, great. Thank you.